Okay, this is section 13.4, motion along a curve, and this is practice problem number 1. Given this particular vector curve, then find the velocity of a particle traveling along it, the acceleration of that particle, and then the two components of the acceleration, the tangential and the normal. Okay, so the first derivative of r is v of t. So that answers the first question, and that's going to be negative sine of t, cosine t, and 1. So there's the velocity curve. Of course, the next derivative of that is going to be the acceleration curve. And the acceleration curve is derivative of negative sine is negative cosine of t. Derivative of cosine is negative sine of t and 0. So there's the overall acceleration curve. So there's the answer to the first two parts. In order to find a t, that's just equal to the first derivative of the speed. So it'll be v prime. Now, in order to figure out what that first derivative of the speed is, we've got to find the speed. So let's consider the speed function. So what is the speed, the magnitude of this velocity? Well, the magnitude of the velocity is going to be sine squared plus cosine squared, which is 1 plus 1, and that's all under the radical. So it's the square root of 2. Notice it's a constant, it's not a function of t. So its first derivative would be equal to 0. And what that really means is along the trajectory of this helix, the tangential acceleration is 0. The reason why, the velocity is constant. It remains the same. It's no longer a function of t, which means it never accelerates in the direction it's going. This doesn't mean there's no acceleration. It just means there's no tangential acceleration. Okay, how about a n? Well, clearly a helix is always turning, and the normal component of the acceleration controls that turn. Remember, this is always going to be equal to the curvature, and then we'll take that times the velocity squared. Okay, so let's find these two things. First of all, the curvature. Well, we've already got the first and second derivative, so let's use the version of the curvature, which is r prime crossed r double prime divided by r prime magnitude cubed. And the reason we're going to use this version is we already have those vectors. So r prime crossed with r double prime, that's just going to be equal to this 3 by 3 matrix. We'll have I, negative j, and k. And then under that is the velocity, negative sine, cosine, and 1. And under that is the acceleration, negative cosine, negative sine, and 0. And we need to evaluate this for the three components of r cross r, r prime cross r double prime. And what are those going to be? Well, let's take a look. We've got, for the I column, it's going to be 0 minus a negative sign. So that's just sine of t for the I column. For the j, remember it's going to be negative. It'll be 0 plus cosine. So it'll be negative cosine of t. And finally, for the k component, it's going to be sine squared plus cosine squared. And of course, sine squared plus cosine squared is 1. So there's the actual cross product of the velocity and the acceleration. And of course, its magnitude is going to be radical 2. Sine squared plus cosine squared plus 1 is 1 plus 1, which is 2, all under the radical. So this will be the magnitude of r prime crossed with r double prime. So that's the numerator up here, radical 2. And then the denominator is just going to be the speed cubed. And of course, the speed is just the magnitude of the velocity vector, and we can see that that's also going to be radical 2, but we're going to cube it, so it'll be 2 radical 2, and of course that's going to mean the overall curvature is 1/2. So that's the curvature, and then finally we just need to multiply the curvature by the speed squared. So this is going to be 1/2. Of course, the speed was the magnitude here, that was radical 2, and squared is 2. So we're going to end up with a normal component of the acceleration of 1, which means the acceleration in the normal direction is going to be 1 because it's 1 times the unit normal vector. So in essence, there's an inward acceleration of 1, and that maintains this constant turning of the helix while it moves upward, and everywhere along its trajectory, its velocity remains constant. So there it is, completely deconstructing motion along a helix.